I hope my screen is visible to you all. A very good evening. Welcome to the week 4 live session for the doubt clearing of aluminum based alloy and metal matrix composites. I am Ananya. I am a PhD scholar in the Department of Mechanical Engineering at IIT Delhi. In today's week, the main topic was precipitation hardening, so we'll be talking about that. But as I promised in the last session, that we'll be first discussing about the current semester assignments that have already been submitted by you all, the first and the second week assignments. So I'll be present the answer of those. We'll discuss if we have any doubt, and then we'll discuss about the week 4 assignment of previous year so that you guys can have an idea how what type of questions may come. Then we'll discuss about a few topics and your doubts. So let's start. So yeah, it's for week 1, so you guys can just simply unmute yourself and tell me the answers. That will be better. So the first question was, which of the following sentences are correct about pure aluminum? Yes, please.
The tensile strength of pure aluminum decreases with decreasing purity. Ductility increases with increasing purity.
Yes. So the third option is more correct. Actually, the ductility is more in the pure aluminum, because aluminum is an FCC type of lattice and it has much more ductility in its pure form. The second one is, which of the following is are incorrect about aluminum and its alloy? So be careful, it's
Excuse
incorrect.
me, ma'am.
Yes.
Ma'am, isn't this second statement also correct?
With decreasing the purity means the percentage of aluminum is lower, and due to that the tensile strength of pure aluminum decreases. Okay, so in terms of ductility you can say that due to the decreased ductility the tensile strength decreased, but it's not always true, because we are also doing some strain hardening and we are mixing the alloying element to just enhance the strength. So you can't say like the tensile strength will always decrease if the purity is decreased. You can say the ductility can decrease if the purity is decreased, but we can't comment on
Okay,
the
ma'am.
tensile strength directly, as
Okay, ma'am.
the strength will be a result of the alloying elements also, how they are bonded and how the hardening and all those things are taking place. So that's why we can directly say the ductility will increase with increasing purity. That's why it's correct. The next one is,
Ma'am, but we can say the ultimate tensile strength. We can talk about that.
the ultimate tensile strength, yes, as I said, you can say the tensile strength will decrease, but you cannot directly comment on that just by this sentence of aluminum's purity is decreasing. So it's like we often do the hardening and the enhancement of strength by some other means, some other post processing and alloying as well. And that's why I said you can't comment on that directly. It's true, but there are a lot of other facts also connected to this one, this tensile strength. But the ductility you can comment.
Okay, ma'am.
So next one is, which of the following is are incorrect about aluminum? Yes, it's FCC, but is it a paramagnetic or ferromagnetic?
Paramagnetic.
So the incorrect one is ferromagnetic. And is there anything other, or is there other option?
The corrosion resistance is good, but poor conductor that one.
Okay. And also, corrosion resistance is also high. So the next is the impurity that causes excessive edge cracking during hot rolling of aluminum sheets.
SI.
Yes, silicon. The next one is, what is the purity level of aluminum grade recommended to use in electrical conductors? It's 99.5%. Next is, in Bayer's process, very fine AlOH3 particles are added to form. We can just show the answers. Nuclei of for the precipitations of pores AlOH3. In Hall-Héroult process, contact between the anode and bath is interrupted by the gas film when the alumina falls below 2%. Next is, which of the following methods are used to improve the gas impurities from aluminum melts? Yes.
Inert gas purging by using degassing tablets or by addition of fluxing agents.
Not
Uh,
fluxing.
why not? Uh, like I
Fluxing can
remember.
also be done, but yeah, it's fine. Fluxing can also work because that was also used to eliminate the hydrogens, I think. One or zero after decimal point, so it was ingot and finished. Simple. Addition of silicon as an alloying element is useful because improve fluidity, reduces the solidification shrinkage and reduces the melting point. In the following question is are, please tell me the answer of this question. This was already discussed in the class.
A is false, R is true.
So next is, this is for week 2. So when Al14Si alloy cooled from 700 degrees centigrade, so basically primary alpha aluminium, pro-eutectic silicon and eutectic silicon will form. Then addition of small amount of chemical modifiers will just deactivate the TPRE mechanism. We have already discussed about it as well in the class, and prevents the attachment of Si atoms.
Excuse me, ma'am. Ma'am, can you please explain the first question of week
Yes.
2?
So in first question, it said 700 degrees centigrade. So first of all, you have to have a TTD diagram or the phase transformation diagram for Al14Si. Then you'll see how the curve is coming down. The curve will somewhat coming down like this. If this was the zone, so if it comes down like this, so the area it's going through at the last stage when it is at room temperature, it will have all the phases present inside it. So this was the primary one, so this was the eutectic and alpha one, and here the pro-eutectic will form. So that's why when it will cool down from 700 degrees centigrade, it will have all the phases present inside it. So you have to have the you have to know about the phase transformation diagram or TTT diagram for this particular alloy. Then only you can comment on this. Is it okay?
Okay, ma'am.
Next one on cooling ALSI alloy with a lower cooling rate during solidification. So the ductility of the alloy decreases. So it's basically when we cool down very fast, the ductility will decrease because the hardness will increase because of the small grains. But even when you cool down slowly, at that time also the precipitates will form. It will try to have a what say equilibrium phase. So and for that, due to the precipitations, the ductility will always decrease. The morphology of eutectic SI will be coarse and needle type. So as I said, when you cool down very fast, rapidly, then the particles or grains will be smaller. But when you cool down slowly, the grains will be coarse and the hardness will be less. But still the ductility will always decrease. The next is hypereutectic ALSI alloy are known for their. So hyper means the amount of Si is more. So due to that, obviously higher hardness, because the Si or alpha Si will always try to show the TPRE, the twin phases, and even under the optical microscope you could see the twin planes, and due to which the hardness increases. So in hypereutectic you'll always have higher hardness. And this more to good castability and higher wear resistance. I think you had a doubt on this question in the last.
No, ma'am. It was on the first question.
Okay, okay. What do the last two digits so it doesn't have a significant meaning? And then in elastic interaction, the strain field associated with interstitial solid atoms will interact with both edge and screw. Next one is, which of the following statements is are correct about solid solution strengthening in aluminum alloys? So what will be the answer? What will be the answer? Shailesh, you can also unmute yourself. So the answer will be 2 and 3. The interstitial solute atoms, if they are larger than the interstitial space, so they will impose a compressive stress field in the lattice, because all other atoms present inside the lattice will try to move in the outward direction because of the larger interstitial atom, but the overall lattice will not allow them to move outward. They will try to make the surrounding atom place in their own position only, so they will feel a compressive stress, and the dislocation motion is hindered due to the diffusion of solid atoms into the dislocation core. Then strengthening of aluminum alloys through electrical interaction is mainly due to, it's because of the valency difference in the solute and the parent. This is why there will be a dipole moment created inside the lattice, some positive and negative end, and due to which the dislocations will feel difficult to move through the plus and minus poles. Stress required for dislocation to move through the APB will increase with a decrease in APB spacing. And the last one is drag stress on the interaction stress between the solute and the moving dislocations will increase when the strain rate increases. Is it fine? Okay. So, and also the dislocation velocity, yes, dislocation velocity it increases. So then I have a graph. It's not very clear though, but we have gone through some experiments where I got this graph. So it's like a stress strain graph. It's basically a force and displacement graph which you can convert into the stress strain graph. So it's showing after the upper hill point, the aluminium, it's for aluminium, it just had a breakage and fracture from this point. But if you see a mild steel or steel stressed in curve, there you can clearly see the serration part. So that's why I wanted to discuss about the serration part again in this video, in this session, a small part. So it's like in the last class we have discussed, right? In steel, the carbon and nitrogen are the solute atoms, and they preferably sit in the interstitial position because they are very small in size. But for aluminium, the solute atoms sit in the atomic lattice position, due to which it always feels difficult to find a nearby next vacant place to jump into that for the movement of the solute atoms to restrict the dislocation movement. But for this type of steels, if there is a dislocation and this as the solute atoms, so this solute atoms feel better, or they don't feel that much stress or restriction to move forward inside the lattice. So they can move very easily, not very easily, but easier than aluminium atoms to catch the dislocations. So what happens in steel is when the dislocations try to move, they uh, got the restriction of the solute atoms. In steel, it's faster because the solute atoms are moving through the interstitial positions which are always vacant. But for aluminium, the solute atoms are moving through the substitutional positions which are not vacant always. They need to find the vacant place, and also they need more energy to jump into the vacant substitutional place. So this is why when the dislocations move through an aluminium, they don't feel that much restrictions like steel. So that's why if you see the stress strain curve for steel, the serration is very much observable, means it's noticeable. But for aluminium, it's not always noticeable. Even if you are working with a 600 grade or 6000 grade or 4000 grade, where the magnesium is present with a higher amount, and as we know the magnesium is responsible for the serration in aluminum. Even at room temperature, the aluminum doesn't really show the serration every time. It shows, but as you see in the last car, it didn't show the serration. But at that time when we experimented with steel, the steel really showed a curve like this. I don't have that curve right now, but if I can manage to show you in the next class, we'll see how much defined and noticeable the serration is inside the steel. Because we can imagine, right, the interstitial solute atoms are moving and restricting the dislocation paths easily. They feel easier than aluminium's substitutional solute atoms. So this was one thing I really wanted to discuss with you. So now if we have any particular doubt, you can ask. Otherwise, we'll go through one by one topics. Anyone? No doubt from this semester, this lecture week?
No, no query.
Yes?
No query from us.
Sorry, I can't hear you. Just breathe.
No query from my side.
Okay, okay. So in today or in this week, the main topics were last lecture from week 3 and the first 2 or 3 lectures from this week, because after that from fourth or fifth lecture, those were more particularly talking about the precipitation hardening for different alloys. So that is a common thing, you can read about it, but the main thing is understanding the phenomena how the precipitation hardening is taking place. So if other two of you have any doubt.
Yes, ma'am. I have a doubt. Like I had heard sir saying in the classes that GP zone formation is very important for the stable homogeneous precipitates to form.
Yes.
Ma'am, like my query was like I have seen later that in some places a precipitate is formed, but we are not talking about the GP zones. And like there are two phases like the theta 1 theta and theta dash. Many a times like we don't speak about theta.
Okay, so what happens is in aluminum particularly, these things are important, and also the formation of GP zone, theta double prime, theta prime. These you really can't find that much noticeable time in between these phases, like to distinguish between these phases at the time of simulation or the testing. Even if you are performing a precipitation hardening test, you will only have the result of the precipitations like the theta phase, and the if it's overaging then the hardness will decrease. So it's not like that. This is why people don't really talk about GP zone and theta double prime, theta prime, because these are not noticeable that much at the time of simulation, at the time of testing. But we why we are talking about it is because we are concentrating upon the aluminum alloys, and these are specific for aluminum alloys only, because for steel and other alloys these things are not that much important. These things hardly takes place. So this is why you can't find these things anywhere else. If you also just Google search it and find it, you'll see these things are only for aluminum alloys.
Yes, ma'am.
So this is why this graph is very specific for aluminum alloy. This double peak graph for hardness, because for steels it's a single peak graph. There will be an increasing hardness, then overaging, and then decrease. But this type of graphs are found in aluminiums only. And also when we do precipitation hardening, we really don't consider this GP, theta double prime and theta prime. If we want to go deeper in that particular zone, in that precipitation hardening, then only we can see these things. So but as you guys are learning about aluminum alloys, so it's important for you to know each and every point about it, this GP zone and the theta double prime, theta prime. So any other doubt apart from this?
Also, ma'am, there was a point where we were discussing about how the dislocations are moving around a precipitate, like how there is interaction between their field, like some curvature is forming. Can you explain that in a little detail? I didn't get it.
Yeah, okay, fine. So let's do one thing. If you don't have any other doubt, we'll start from the beginning, then we'll come to that point so that we can cover all the topics, all the points.
Sure, ma'am.
So okay, so in last class, as we saw in the first half also, there was serration. So there was for a particular strain rate. Normally, what happens is when the solute atoms move, when the dislocations move, the solute atoms try to catch up. But when the rate is too high, that there is no thermal activation for the dislocations, but there is a thermal activation for solute atoms. The solute atoms start moving rapidly, and the dislocations really can't find enough time to get diffused and or to move inside the lattice, and this is what was giving rise to the sedation and the quadrille atmosphere and those things. So that was a part of hardness increase, but that was not cert. That was having a typical uncertainty. That's why we were trying to avoid those things. But normally, in normal tensile testing, without even applying any external temperature, you'll see those type of sedation in steel also. This was a particular thing, and then we were talking about the precipitations. So precipitations are like we are first increasing the temperature of the alloy, then we are lowering down the temperature, and how we are lowering down is we can quench it in water or oil, like we are just lowering down the temperature rapidly. We can lowering down the temperature very slowly, that is slow cooling rate, and quenching is high cooling rate. For high cooling rate, the grains which were there at the time of melting, they really don't find enough time to grow inside the lattice, and this is why for quenching we get smaller grain size. But for lower cooling rate, the grains find enough time to grow inside the lattice after nucleation. This is why in lower cooling rate the grain sizes are more, and also as the grain size is smaller, for quenching we get more hardness. So for fast cooling we get smaller grain size and more hardness, because the number of grains increases and the number of grain boundaries increases. But for slow cooling, it's just opposite. Time for growth of the grains inside the lattice, and this is why hardness is lesser, because the grain boundary is also lesser in this case. So this is a normal thing. The next thing comes for alloys. For alloys, the alloys are also called the solute solution. So we are just mixing 2 or 3 components together. That's why it's called solute solution. When we mix all the alloying elements with the parent atom, alloy with the parent atom, and then we heat up this to a elevated temperature, all the alloying elements mix very properly and uniformly, and when we cool down suddenly, the uniformity may sustain inside the lattice, but what happens is the solute solution will having a much more uh, percentage of the alloying elements than it can sustain at normal room temperature. If we do the solutionizing or solute solution treatment at lower temperature, we can't really add much more alloying elements. Otherwise, it will get separated. Means we'll see some precipitations are forming. But when we do it at higher temperature, it can sustain or bear with lot more number of alloying elements. This is why it's called super saturated solutions that we can really have at higher temperature. But when we are cooling down to room temperature, what happens is the SSS is present, the supersaturated solution is present, but at that time this supersaturated is not an equilibrium phase. At the From the name only we can imagine or we can think of it like it's not equilibrium, so it will always try to have an equilibrium position. This is why it will start separating out the excess amount of alloying elements from this, and when it start separating out, that excess amount will form the GP zones. That is very important for this particular topic. And this GP zones then will start grow inside the lattice, and those will try to match the lattice parameters, will try to maintain a coherency with the lattice, and when you'll it will achieve a coherency with the lattice, the dislocations will find difficult to move. Also, the hardness will increase because the coherency is increasing somewhat, means like the uniformity is increasing inside the lattice of that particular precipitate or of that particular phase of theta double prime or theta prime. After that, when it's trying to get the equilibrium, after some times it will get the equilibrium and it will reach at the or theta prime position, the most or highest peak point, and at that time it will have the highest coherency, highest lattice match, and equilibrium phase, and also the highest hardness. But when uh, it's again sustained, it's being holded at that temperature, room temperature or something, it will start decreasing its hardness, because the precipitates, if the supersaturated level is so high, if the alloying elements percentages are so high, then it will just continue separating out the excess amount of precipitates, and at that time it will be overaged and it will give rise to lower hardness. This is what happens. Now this is a all over um, overall idea of the precipitation hardening, how it's really taking place. We just know that for aging, the excess amount of alloying elements come out from the lattice and those form the precipitates. But this is how step by step the precipitates are formed. And what happens inside the lattice is, when there is two precipitates, there are two precipitates, and if the distance between them is lambda, now there is a dislocations which is coming. So maybe the dislocation is like this. It's a symbol of dislocation. It will try to move and overcome this barrier of the solutes. But it cannot move further because there are two solute atoms, or there are two precipitates sitting over here. So first it will try to break them. If somehow the precipitates are not that much strong, then the dislocations can just break it out, and the surface will increase the surface area, and at that time the dislocations will further feel difficult to move this over or overcome this barrier. But here what happens is, sometimes the dislocations get bent to pass through this passage, and it will be like this, and after it passes through, again the dislocations will move, and this is how it overcomes the barrier. And when it overcomes the barrier like this, there will be some dislocations um, leave behind the precipitates, and this is what like, what should I say, a loop of the dislocations really form. So when there will be this barrier of the precipitates, now a lot of one dislocation is coming and it's feeling the barrier, then other dislocations are also coming in a line, so they will be lined up behind this precipitates. So as a result, when this will overcome the barrier, this will bend and pass through the passage, some dislocations will just leave behind and they will make the dislocation loop. It's not really called dislocation loop, but it will create some loop surrounding the precipitates. And these dislocations are having opposite sign. than the solute atoms or the precipitates. This is why this left behind dislocations feel again difficult to move or pass through this precipitates. So this is one phenomena inside the
Excuse me, ma'am.
precipitates. Yes,
Ma'am, this loop that is formed, it's exactly what? Is it like some charge because of some charge, or is it like
not
that
charge. You
tensile?
can say uh, it's a dislocation. Okay, and there are 10 dislocations coming line by or they are just 10 dislocations are lined up behind this particular precipitate, and all of them are coming, and now as this first one couldn't pass through, all they are will be lined up, and after certain time all the tents will be gathered here, and then they are trying to pass through this passage, and at that time maybe 8 dislocations just moved or passed through the passage, but two of them couldn't pass, so they will just make a loop surrounded the precipitates. And because also the dislocations will feel the stress or the drag stress when they try to overcome the barrier, and they need a lot of more stress than normal stress to pass through this type of precipitates and passage of lambda gap. This is why if the lambda is more, the stress will be less, because or vice versa we can say, if the lambda is less, the stress will be more, because they cannot really pass through the gap because the gap is so less. So this is why if the lambda is more, mm, okay, means there are a lot of gap between these two precipitates. So now the dislocations can easily just a small bend can help them to pass through this passage, and the stress will not be that much because stress is something that the lattice is providing to the dislocations to stop their motion. The stress will not be that much, so the hardness will decrease obviously, because dislocations can easily move through the passages in between the precipitates, and this is what happens when we do the overaging. So in overaging, the size of this precipitates will grow, and as a result, the distance between them will increase. Is it okay?
Yes, ma'am. Understood.
Okay. So there are a lot of other type of dislocations movement as well. I don't know those will be covered in the upcoming lectures or not, but if not, I'll talk about it. I'll demonstrate all the other types of dislocations movement uh, using this phenomena, as I said in the previous slide. So here all the things are lined up and bunched up. Dislocation multiplication also takes place. So one is stacking fault. You have already read about it, where the dislocations get broken or give rise to two simple dislocation from one dislocation. And here the dislocation multiplication is going on. There are other types like dislocation loops are formed. So yeah, this thing. So the next was different stress which are uh, there between the solute atoms or the precipitates more specifically, and the dislocations due to which the dislocations feel difficult to move through because of the precipitation hardening, and there were some equations for each case. So there was lattice friction. This is not the normal friction of a particular surface, it's lattice friction. So when the atoms are trying to move pass through each other and these things, so the alloying elements atom and the parent lattices atom are different, so this is why they feel some friction, because dislocation is having the lattice atoms, and the solute or precipitates are having the solid atoms, so they feel the friction force. Then interstitial or interfacial energy is something that's I have drawn. If the precipitate, if this is like this and one dislocation is coming, and if the dislocation is having enough dislocation velocity, and if this precipitate is not formed uh, properly, or the energy is not that much, then it will just break into two pieces or more than two, and the surface area will again decrease, and the dislocation will again find it difficult to cross through. So it's just trying to break the barrier, and as a result it's just increasing the barrier to overcome. Modulus effect is also discussed in the solute atom movement as well. So the modulus of the precipitate and the dislocation is different, as we taught in the strain hardening also, that the solute atoms are having different modulus, and those solute atoms are here making the precipitates. So obviously the modulus effect will be there, by which the dislocations feel difficult to move. Ordered structure is that long chain barrier or short chain barrier clusters. So for long chain barrier, if there is ABB, so it will be difficult for the dislocations to move. Stacking fold energy is also similar, and the new one is the coherence. So there is a lattice mismatch between the GP zone and the lattice, parent lattice, because the composition, the properties, the electronic configuration, everything, and the lattice structure, everything is different in parent and the solute. The parent is making the dislocation, the solutes are making the precipitates. So there will be a mismatch in the lattice structure, and the mismatch is calculated using the lattice parameters of both solute and the parent. Lattice parameters mean in FCC there is a and C value in angstrom. Those are the lattice parameters, and there is a percentage. How we calculate the mismatch percentage, and uh, due to the different electronic configuration and lattice structure, there is a mismatch, but there is no hard and fast particular structure of the GP zones or precipitates, as they will just move, they will just make a type of cluster by bonded with each other, the solutes, and also they will form, sometimes they form compounds of different elements as um, a precipitate. So this is why they always try to minimize the mismatch between them, so that there will be a coherency uh, in the lattice. Coherency means just they are in same phase. Coherence means there is no phase difference. So this phase and that phase are different. So this means the lattice parameters are matching more or less with each other. Each other means the lattice, parent lattice, and the precipitates. And this is how, with each theta or GP zones, with each step, they try to maintain the coherency, they try to minimize the lattice mismatch, and they, as a result, the hardness increases. But after some times, when they achieve the equilibrium position, they don't care about the coherency at all, because first of all, they try to maintain the coherency. But as soon as they separate out the excess amount of precipitates, they will be at a stable position and equilibrium, and they will not at all care about the coherency anymore. So this is because this is why the coherency will be lost, and after equilibrium, due to the tendency of the separating out the excess amount, the overaging sometimes happens, and due to overaging the hardness decreases. As I said, the dislocations will again find it easy to move through because the coherency is lost. Uh, yeah. So for artificial aging, the thing is, the aging is doing at elevated temperature. The equilibrium phase will be achieved, but if the cooling rate is lower, then it will be achieved at a lower rate, or uh, I can say when the cooling rate is fast, these things are taking place very fast. But when the cooling rate is slow, this thing will these things will be noticeable. You can observe the phases differently, the alpha, the theta, the equilibrium phases. um, and yeah, it's about how much temperature we are giving and how much time we are holding the material. Based upon that, the precipitations will form, the precipitates will form, and the hardness will be in the range. And also there were T1, 2, 3, 4 up to 8, I think, or 9. You can just go through it. For 7000 series, people often use it at T7. So as I said, T7, okay, so in T7 there will be an overaging, but T7 is also used for some particular properties. As I said in the first class, it's all about the application where you want to use the aluminum alloy. We don't always want the peak hardness, because for 6000 grades, mostly the T4 and the T6 are the most common heat treatable alloys. Those are available in the market. If you want to go for buying some 6000 grade, people will provide you T6 hardened alloy only. But some people will ask you whether you want T4 or T6, because always we don't want that peak hardness, because sometimes as we are using aluminium, we want the ductility present inside the aluminium, and we don't want that much hardness inside our aluminium alloy, depending upon the application where I am using. This is why, although T6 is the peak hardness, but you'll see that 7000 series alloys are not typically used with T6 condition. They are mostly used with T7 condition. So there are 5.1 and 5.2 as well. So 5.1 is like we are stretching the
Excuse me.
yes.
6000 series alloys, do we use T4?
6000 series are used in T6, but you'll find with T4 as well.
Ma'am, but like that is natural aging. So I mean, like, would it is reaching the peak hardness only, no?
Yes, it will be reaching, but the T6 will have the peak hardness, and the T4 is having always less than the peak hardness.
Okay, ma'am, understood.
So in natural aging, the peak hard the peak hardness we will get after a lot of time, because it's doing at room temperature, so the time needs to be very high. But the peak hard that's why peak hardness is always not achieved. It's never been achieved in natural aging. It needs a lot of time. For T6, as we are providing much more temperature, so with minimum time we'll get the peak hardness.
Okay, ma'am.
In T6 there are also 5.1, 5.2, 5.1. We are just stretching the alloy to relieve the compressive residual stress, whereas in 5.2 we are removing the tensile residual stress by just opposite compressing it. Then there were the phase diagram. So aluminum is the the most easy alloy to know about, because there are no separate phases. In steel, you might be knowing about austenitic, martensitic steels, and there are a lot more pearlite, bainite, a lot of phases. And you'll be puzzled when you'll be knowing about steel because of the different alloys. But aluminium is easier than steel because there are no separate phases really. These are some few phases formed during the precipitation hardening, and even people don't talk about it much, so it's not very much visible at the time of simulation. So we are just learning about aluminum alloy. This is why we are knowing about this different phases. So yeah, if you have any other doubt you can ask, or else we'll talk about the last two lectures. No? Okay. So for lecture 4, from lecture 4, we started knowing about the 2000 series. Then,
Excuse me. Sorry to interrupt, but I had a doubt in the formulas that had been given.
okay.
Those formulas, like there was for modulus effect that explains this phenomena of hardening. There is a B. That is actually what? Is it bulk modulus or Berger's vector?
Which one?
The B in those formulas. Is it like the
Small
bulk modulus?
small b is Berger vector.
Okay.
Okay. So lecture 4. So there were the 2000 series, which was a aluminum copper alloy. Uh, so this was the first series which is heat treatable, and using this series only researchers discovered the hardening or age hardening process. So in this thing the precipitations will form like first the supersaturated, then the GP zone, and then consequently the theta double prime, theta prime, and the theta will form. And the theta, if you consider theta to be the most stable, then it will have the composition of CuAl2, which is the precipitate here. And also there was what should I say, the lattice properties of the GP zones. So that there was a plane, particularly at that plane only the GP zones will form. So that is like a preferable site for the GP zones to get formed. So that is 100 plane for the GP zones to form. So GP zones are kind of clusters. The size of the GP zone, if just increasing, then it reaches the constant, what should I say, the constant thickness of the GP zones, and the distance between those or the thickness of the GP zones will be, what if the size is increasing, then the thickness will be constant, and for that the thickness will be q interatomic distance. If the clusters are surrounded by the aluminum alloys and vacancies, then the size of GP zones will depend upon the temperature. And always the GP zone size of the GP zones will depend upon the temperature. If it's at room temperature, or if it's a elevated temperature, or we are doing the cooling with a slower rate, or we are doing the cooling with a rapid speed. Also, another important point from this to note was the copper content doesn't really affect the GP size, but it affects the number of GP zones. So, at particular plane of 100 only, the GP will form. If the size is increasing, the thickness will be constant. It will be few atomic distance. But if the Cu or the copper as an alloying element is much more in content, the GP size will not get increased. It will be same, but the number of GP zones will be increased. So there was an example of the alloy of aluminium 4 copper, where the number of GP zones were somewhat around 10 to power 14 to 10 to power 15 per millimeter cube. So it's very large, because also the size of the GP zones are few interatomic distance. The spacing between them will be in nanometer, and if the temperature is high, then it will get lower down. The next phase was theta double prime. So these will again have a shape. So for aluminum copper alloy, this will have a disc-like shape, and the size is larger than the GP1 or the main GP zone. Then the diameter of the plate or disc-like shape was given, and the thickness fewer atomic distance again, but it's obviously more than GP, because the GP zones are trying to get the equilibrium phase, so they will try to grow, they will cluster more number of precipitates, and this is how they achieve the equilibrium phase. So obviously the size will increase. Then when the GP zones are trying to increase their size, at the same time they are also trying to maintain the coherency. They are trying to maintain the uh, minimum lattice mismatch between them, but at the same time they are trying to get the equilibrium, and they are more concentrated, or they are concentrating about upon the equilibrium phase, to get an equilibrium phase more than getting coherency with the lattice. This is why the coherency will be decreasing with each step or each phase. So this after this, the theta 1 phase will come, which is a semi-coherent phase, and after which the theta comes, which is the equilibrium phase. These phases are similar for each alloy, but the shape, the size, thickness, these things are different for different alloys, because these phases are made of different compounds. So depending upon the atomic layer, atomic size, their valency, and their properties, the GP and theta phases will be determined, and their properties and their sizes. Like for aluminum copper, the theta phase will be the equilibrium. As you know, it's copper aluminum 2, but it will have a tetragonal crystal, and it's it will have the more its equilibrium, so coherency will be lost, and as a result, from theta phase or just after theta phase, the hardness will start decreasing, because it will be overage. So in next, it was like 2024, as I mentioned in my previous class also, 2024 and then 2014. These are very well known aluminum alloys used in aerospace components like fuselage and different engine parts. Um Next is having and also this things are, or this 2024, 2124, 2014, these are used for different heat treatments, because they are heat treatable alloys. So also that was mentioned for which this heat treatment, how much will be the yield strength, and how much will be the percentage of the proof strength, or similar thing. So T8, T3, T4, These things are the most commonly used heat treatments for copper, aluminum copper alloy. The next one was for 6000 series. As I said, T4 and T6 are the most common heat treatment processes for this series, but you will find people are using 6000 series with T6 condition only without even knowing about it, because when you go for buying a aluminum alloy na, of 6000, they will provide the T6 condition only. Very few company will ask you about whether you need T4 or T6, because you may have an application where you do not need the peak hardness, you need some type some uh, percentage of ductility as well. So it's like that. So if you want T4, if you don't want the peak hardness in your 6000 series, then you need to let them know that you don't need T6, you need T4, otherwise you'll be provided with the T6 6000 series only. So for 6000, the process will be similar, the phase formation and the mechanism will be similar, but as the 6000 is the magnesium and the silicon and magnesium alloying of aluminium, so the precipitate will be different. It's magnesium to silicon, Mg2Si precipitates, and for those the phases are called beta. So it will be like, okay, let me write. For 6000 it will be like supersaturated solid solution, then Gp, it's common. Up to this it's common for all the alloys. Then comes the beta dash, and then beta. Mg2Si is the precipitate, and after this the overaging starts and the hardness will decrease. So the Gp zone for this is spherical in nature, in shape, and also as it's spherical, so it gets elongated when you continue the aging for longer time, and also towards the 100 direction the elongation will take place of the GP zone. And also for overaging or for long time aging, if you increase that aging time or the temperature, this elongation will be carrying out until the GP zones are becoming a needle-like shape structure. The GP zones are also consist of the magnesium and the silicon ions, obviously. Maybe the compound of magnesium and silicon atom will not get formed. So the GP zone may not have Mg2Si, but it will certainly have the Mg and Si. So as we know, GP is the cluster of atoms. So all the solute atoms which are trying to move through the vacancies, they will just come together, make the cluster of Mg and Si. After that, when they try to have an equilibrium phase and position inside the lattice, they form the Mg2Si compound, which is the precipitate. Then, as was mentioned, in beta prime only, the Mg2Si starts forming, and it will show the semi-coherency as they are more concentrated upon making equilibrium phase than maintaining the coherency. The length of this phase is typically in micrometer. 1 micrometer diameter is zero point 0.1 micrometer, and then the beta will form, which is having the peak hardness or the most hardness. It's again plate shape with the lattice parameter of in nanometer. Next, uh, the temperature range at which these things are carried out are typically in 170 to 200 degrees centigrade, and the GP zones dissolve at 225 degrees centigrade, which gives us the Solvers line. Means when you cross this line, the theta the beta prime phase will start forming. And also the magnesium and the silicon ratio will be at particular first stage when the GP zones are forming, At that time, the Mg and Si atoms will just come together, sitting together, making a cluster. But after some times, when the GP zone, if this is the particular duration of the GP zone, at this phase, this will be like this. At this phase, there will be a certain percentage of magnesium and silicon. They are clusters. They don't have an uniformity and they don't have any particular compound in the cluster, but they will have a certain percentage or ratio of magnesium and silicon, and that is more likely like 1.73 is to 1. And if apart from or beyond this ratio the silicon is present, then that will give us more strength in the GP zones, because we know silicon gives rise to hardness and strength because of its structure. And but at that time the corrosion resistant will be lowered down, which is also a good and important property for aluminum alloys. The aluminum 6061 is a well-known alloy used in aerospace components, many aerospace components, and spacecrafts, satellites. As I said, this 6061 is also used in T6 and T4, but mostly commonly used in T6, unless until you specify the T4 uh, heat treatment. Then this T6 gives rise to the peak hardness, as we will be going through the artificial aging in T6 condition, and the uh, peak hardness will be given by proper amount or percentage of magnesium and silicon only. And also some chromium is also present in the alloy, but it will not take part in the uh, what's it precipitation. It will just give rise to more grain refining. The peak hardness can be hampered if the silicon percentage is more than certain amount. There is always a range of part of alloying elements in a particular alloy. So if somehow the silicon is beyond that range, the peak hardness will be hampered. May the hardness get increased, but that may not help in our particular application. So we have to be very careful when we are alloying something, we are mixing something in the aluminum as an alloying element. Next was the 6262. The composition was given, the magnesium silicon is the main alloy, chromium will be there, copper is also there. That alloy exhibits the good missionability, and that is having a quench sensitivity, and which is low. So quench sensitivity is nothing but when we are quenching, how it's behaving, like how it's separating out the excess amount of precipitates. If the quench sensitivity is low, means when we'll be quenching, the separating out the alloying element will not be that much. If it's quench sensitivity, if it is having high quench sensitivity, means it will be separating out the most of the excessive elements. So it's just like we are quenching at room temperature. So we are quenching the supersaturated solid solution, which is having a lot of alloying elements mixing in them, which is not having an equilibrium phase. But if the alloy is quench sensitive, quite high quench sensitivity, then at the time of quenching, it will only try to have an equilibrium phase and separating out the excess amount of alloying elements. So this particular 6262 is having quite low quench sensitivity, which is good sometimes. So often worked by extrusion, and chromium is here also just giving us some grain refinement, means grain growth. Then it's used in T5 condition or T9 condition. The proof strength and the yield strength was given, and other alloys are 6061, 6063. These are having quite good surface finish and can be used for different applications like anodization. Anodization is in Apple mobile phones, you'll see at the back side there is an Apple logo. So it's nothing but the anodization of some aluminum alloys or other type of alloys. So the alloys which can give rise to a particular color with a good surface finish, those things are used for anodization. Just depositing some very little amount of that thing with a particular geometry. How we are providing the masking means we are just covering the phone and keeping that small apple portion open, and we are just doing some anodization, so due to which the electrodes will get corroded and the corroded material will get deposited onto that uncovered portion over the phone surface. This is how the logos are printed behind the phone, mobile phones or tabs or computers. Next comes this 7000 series, which is a zinc, uh, which is having the zinc as the main alloying element. The precipitation sequence is again same, but again it's having different notation only. For 7000 series, the notation is eta. So it will have, okay. So for 7000 series, we'll have SSS, supersaturated solid solution. Then we'll have GP zone. This GP is common for every type of alloys. Then we'll have eta prime and then eta, which is an equilibrium phase, and after eta it will start getting the overaging precipitates. Means more hardened precipitates will actually minimize, lower down the hardness. So there, mm, we had an example of 7075, which is the most popular 7000 series alloy. I showed it in one of my previous classes. This 7075 is also widely used in aerospace and aircraft components, in satellites as well. Mostly the 6000 series are used in optomechanical components, and the 7000 series is used for the body structures, for the body of the aerospace. Few parts for typical applications. This 7000 is also used for T6 condition, where the artificial aging will be taking place. So there the artificial aging is carried out at 120 degrees centigrade, keeping it for 24 hours, which gives rise to the peak hardness at T6 condition. The quenching rate uh, will be one parameter which will be influencing the precipitate sequence. If the quenching rate is slow, the precipitate will form directly, means as you could see in the graph also in the TTT. If you are bypassing the nose, we'll get the precipitate here. The grain size will be smaller, grain boundary, number of grain boundary increases as a result, and hardness also increases. But it will have the GP, theta prime or eta prime or beta prime and theta phases. But for this thing, when it's crossing the start position and the end position coming down here, like the slow cooling rate, there you'll find bigger size grains, because the grains get times to grow, and also number of grain boundaries will be decreased as the grain growth has taken place. But here you you cannot find a noticeable GP zone or theta prime, theta, it will directly give rise to the equilibrium phase, because this is something. So when it will cross this thing and come here, it will have alpha, theta and theta prime all at a time. So it's the beauty of the TTT diagram. For steels, the TTT diagram is more interesting because that has a lot of phases and you can really play with the phases, bypassing the nose with different cooling rates, or just touching the nose, or how you're touching the nose, that much phases will be formed at the end. So those things are there, but here there are no such phases. There are only few phases which cannot be observed, which are not distinguishable properly, and also at the time of precipitation only. So it's pretty easier. So yeah, up to this part, uh, it was covered. These all topics were covered in the week 4 lecture. So I think I have covered the lecture 4 and 5 in this, and lecture 1, 2, 3 was all about how what is the mechanism of the precipitation. So if you have any doubt, you can ask. Otherwise, we'll see the previous semester assignment. If you don't have any doubt, I'll ask questions then.
Yes, ma'am.
So should I ask, or
Ma'am, it's clear from my side.
okay, okay. So others also, I hope it's clear. No problem. So we'll start seeing the questions from previous semester. This week's lecture was pretty easier than the last week, I felt. So yeah. First question is, for precipitates to form in an alloy, what will be the answer? Solid atoms should have limited solubility in the parent metal at room temperature, or solid
Yeah,
atoms.
and their solubility should like increase with increasing temperature.
Yes. So that the supersaturated solid solution can form, because if the supersaturated is not formed, then we cannot have the precipitates anywhere. So we always want that supersaturated to get formed, so that at the time of aging, or just holding the material at the lower temperature or room temperature, or just keeping the material in room temperature, it will we will have the precipitates. Then it's a formula based question. Increase in strength due to coherency strength of precipitates and matrix will be related to volume fraction, as it's about the formula, so it's fine. It's f to the power 1 by root f. The next question is, what does T temper in aluminum alloy refer to? T4. T4.
Ma'am, like it's second one, solution, cold working, natural agent.
Is it second one?
Oh, sorry, first one. Yeah.
So there is only one difference in T4 and T6. T4 is in natural aging and T6 is the artificial aging. Then is in which of the following case of quenching medium, precipitates are much finer in the alloy, is subjected to same solutionizing and aging temperature.
Water quencher.
and hardness of the aluminum alloy decreases during overaging heat treatment because any guess?
Formation of incoherent precipitates.
It's as you see, the precipitates are growing at the time of overaging. The lambda is increasing because the size of the precipitation is increasing. So the size is increasing means coarsening of the precipitates. Always
Yes, ma'am.
remember, wherever there is coarsening or there is a coarse structure means the grain sizes are more. So at that time the hardness will decrease. Wherever there is fine grains, fine precipitates, that is that will always have high strength and hardness. Because in fast cooling we get the fine grains, which help us in more hardness, in getting more hardness. And for slow cooling we get coarse grains. So here also you just remember in that way. And also the formation of incoherent. So it's true that the incoherent precipitate has already formed in case of equilibrium phase, so it's okay, it's correct. But the main thing is coarsening of the precipitates.
Ma'am,
Yes.
ma'am, there's a doubt. Like, I read that the coherency comes back after overaging. So, like, after overaging, shouldn't the last option not be there then?
After overaging, at the time of peak hardness aging or at the time of theta phase, the coherency is already lost. It's only having the equilibrium which is giving us the peak hardness. And after that, how the coherency get back to the lattice?
No, ma'am. I mean that the precipitates will have its some proper lattice structure, which
Yes.
is somewhat similar to the parent lattice.
Okay. So at the time of equilibrium phases, na, there was the coherency was lost. It was only having the equilibrium. So after peak hardness, the overaging comes. So the coherency is always already lost. It's already incoherent. So there
Okay,
is
ma'am.
no way to get back the coherency because the equilibrium even it's not there, because the first preference for the solute atom or the precipitates is to get a equilibrium phase. And for getting the equilibrium they are just making the lattice mismatch lower down and making or arranging themselves in such a way that there is a coherency maintained in between the lattice and the precipitates, but their actual motive is to get a equilibrium phase. So as
Yes,
the
ma'am. Understood.
coherency is already lost, so there is no way to get back. Then, when the precipitates shear out by dislocation, then strengthening due to an increase in surface energy is directly proportional to the volume fraction of the precipitates and directly proportional to the particle matrix surface energy. It's okay?
Yes, ma'am. This is from the formula, isn't
Yes,
it?
yes. And apart from formula also you can imagine the thing has been broken down, the surface area has been increased. So surface energy is something associated to the surface area. From the name we can suggest, right? So if the surface area is increased, so surface energy will also increase. If the surface energy is increased, so dislocation will find it difficult to move. So it's
Yes,
directly
ma'am.
proportional. Then when the aluminum alloy aged beyond the peak aging time, then
The strength and hardness decreases, but ductility increases.
yes, and interparticle spacing also increases. as I said now, the lambda will increase as the
Yes,
precipitates will start growing farther. Then when dislocations move to the ordered precipitates, then strengthening will occur mainly due to the formation of it's the easy. It's because of the antiphase boundaries.
yes, ma'am.
The next one is which of the following is the correct order of the aluminum copper alloy?
Triple S, GP1, theta double prime, theta prime, and theta.
Yes. It will always be like this only, but remember when the cooling rate is low, these things will not be distinguishable. You can say that GP, theta prime, this will not be present really. There will be only the theta and the alpha phases. But for fast cooling, we can see at the time of aging. What does T652 aluminum refers to?
Like strain relieving by compression.
Yes, because we are just releasing the tensile residual stress. So yeah, it's done. If you want me to discuss any other topic, otherwise I'll just quickly go through all the topics again up to lecture 3. The graph of this thing is also important. Remember what is there in the x and y direction of this particular graph?
Hardness and time.
It's hardness. It's basically law of time, but it's and also the phase diagram. The TTT is also pretty much easy, whether it's this or this, and the phase diagram is also uh, not that much tough for aluminum. That we call it as hardness type. Okay. I asked for the lecture and those things. So did you get any? Uh,
Yes, ma'am. I wanted to inform you we got all the lectures till now.
okay, good that you got it good. Okay. So yeah, that was the TTT diagram. Then the T1 was the quenching from an elevated temperature shaping process. So first the elevated temperature shaping process, then quenching from that, and then natural aging. T2 is quenching, and after that we are doing cold working and NA, natural aging. In 3, first the quenching and then deformed to a what's it at a certain extent and elongation and then natural aging. T4 is yes,
Excuse me, ma'am.
yes.
Ma'am, I had a doubt. Like, say for example, how do you distinguish? You said that we depends upon the application whether we do T4, T6, etc. But like, say for example, some of the aluminum alloy precipitates are not very stable. So, how do you pick which heat treatment is better for it?
Okay, so heat treatment is giving us the peak hardness by quenching and then shaping and then artificial aging. So before heat treatment, what comes is the alloying. In heat treatment, the first step is solid solution hardening or solid solution aging. There we are mixing the alloy percentages. So how much we want to get, how much precipitates we want to get, depending upon that we mix the alloying elements. Then only we can get the particular hardness. It's not like if you see carefully the alloying element percentages in different alloys, you'll find there is always a range of each element. It will be written like this. For 1 second, if it's a aluminium 6000 series, the aluminium will be at this percentage, at this range, Mg in this range, silicon in this range. So there is a range for each alloying element inside a particular, even if that is a 6061 alloy, there will be a range of this materials. So if you want to go for just if you want to go for the peak hardness, they will mix certain amount of Mg and Si. So the manufacturer of a particular alloy, they know, and they know how much amount of Mg and Si needs to be present inside that 6061 to get the peak hardness. If we want some overaged things, they will mix more Si or more Mg depending upon their calculation. So these all are experimental basis. They all are based upon the experiments. These are experimented, and then people got to know how much percentage is needed for how much hardness. It's
Okay,
not
ma'am.
like the heat treatment is the only thing that we can change and to change the hardness. No, it's the important most thing is the alloying percentage.
Okay, ma'am. I understand.
Yeah, the alloying percentage, the time for which you are keeping the material for aging, then how much shaping, like how much cold working you are doing, how much residual stress is there inside the material. These things, these all things are uh, previously calculated, and this is why we are having that particular data of this much proof strength, this MPa yield strength for this hardness heat treatment. You'll find if you go deeper, you'll find the peak hardness value we are getting for a particular heat treatment process for the particular alloy. The alloying percentage is fixed at that time. If somebody is telling you that 6061 is having the yield strength of this much MPa, which is a value, then the alloying percentage are fixed. There you can't find this sort of ranges. It's like that.
Yes, ma'am. Understood.
So then the T5 was having the quenching, shaping, and artificial aging. T6 is the most common one, quenching, and then a artificial aging. T7 is the overaging. T8 is a cold working and over artificial aging. T9 is the artificial aging, and then we are doing the cold working. 10 is the quenching from elevated temperature shaping. So first we are doing the shaping, then quenching, then again cold working, and then artificial aging. And these 10 are the heat treatment processes. But again, under each heat treatment, there are this numbers 00. Sometimes you file 00, then 51, 43, 52. These things denote the type of post process again carried out to the heat treatment. Aging is nothing but we are giving the alloy a particular time to uh, separate out the excess amount of alloying elements.
No, it's like giving some stress relieving time because the allowing elements will be adding to some strain or something. So you're giving it time to just relieve.
Sorry, can you just repeat your voice?
Ma'am, like it's just like giving it some time to relieve the strain that it has.
Yes,
Maybe there
yes,
is the allowing element to add
you
to
can
it.
say that.
Okay.
Give it some time to relieve the strain by suffusing a specific amount of precipitate.
Yes, ma'am.
Up to this point, if you understood each and everything about the serrations, then the strain rate, then this the first I drawn today, the precipitates, how the dislocations move through the precipitates, the dislocation multiplication, dislocation loop, then you'll easily understand the rest of the lectures, because these were the most dangerous part about the metal science up to the phases. If it's done, then afterwards you will not find that much difficulty.
Okay, ma'am.
The formulas are a bit tough to remember. Okay, so if it's done, we can stop it here also. If you have any further doubt, we can discuss about the previous classes anywhere.
No, ma'am, it's clear for me till now.
So at the time of tension or tensile testing, now you'll find the serration marks on the pieces. If I could find, I'll show you in the next class. In the tensile
Sure, ma'am.
in the
Ma'am, like, will it be on the
yes.
sample itself?
Sorry.
On the sample itself, on the
Yes, on the
cracks?
sample itself. It's
Okay.
said na, for sedation the surface roughness is hampered. The
Yeah,
surface
ma'am.
finish is
It
hampered.
increases.
There will be some
Yeah.
surface roughness. So
Yes, yes, ma'am.
the serration lines or the PNC bands are visible from outside. I don't know how
Yeah.
much I can capture through the camera, but using naked eye we can see the lines. If this is the tensile sample, this is if this is the gauge length of the tensile sample, if the breaking has taken place like this, so there will be strips like this, visible strips, which are the PLC bands. This is why these PLC bands are important.
Yes, ma'am.
In aluminium, due to the color also, it's visible. It's very properly visible.
Yes, ma'am.
Do you know when we carry out the tensile testing, we take a particular dog bone structure only. Then only we can say it's a standardized testing. So there is a ASTM
Yeah, ma'am. I heard about it.
standard which you need to follow if you are going for a tensile testing. So why it is so? Why the sample looks like this?
I guess it's because it's easy to focus the stress in that thin area, like that
Yes,
dog
this
bones
portion
neck.
is called gauge length.
Yes, ma'am.
So we want we why we do tensile testing? To see how the fracture is taking place at the time of simulation, to see how the stress concentration is taking place, is acting the important role for the breaking or fracturing inside the taking place inside the material. So there will be a ductile fracture or a brittle fracture. So for that, we make this thing with more diameter, so that, and this portion with less diameter, so that when we pull it like this, the stress concentration will be dense in this portion. So here will be lesser stress concentration, and here the stress concentration will be much more, so that the braking will be taking place at the middle portion only, so that we can analyze it for the visual and the simulation uh, perspective. So this is why the tensile sample is made like this. And for compression testing, the samples are like this only, cylindrical, for a particular L by D ratio when we go for the compression testing. So these are also very important if you are going for any experimental works.
Okay, ma'am.
Okay, so if it's done, we can stop our today's class here. Okay.
Sure, ma'am. Thank you.